quantum mechanical model of atom. Quantum mechanical model of atom. In this session, I am going to teach the filling of orbitals. Filling of orbitals. Already you know that in previous class, the energy of orbitals, the order of energy of orbitals, 1s less than 2s, 2p, 3s, 3p, 4s, 3d. The order of, the increasing order of the energy of orbitals. In this class, the filling of orbitals. How to electron fill in the orbitals. In an atom, the electrons are entered the various orbitals. For example, carbon, atomic number 6. How many electrons? 6 electrons are there. So S electron, S orbital having maximum 2 electrons. So 1s2. Remaining 4 electrons. So 2s2. And remaining 2 electrons and 2p2. In an atom, the electrons enter the various orbitals. The electron filled in the various orbitals according to alpha principle, Pauli exclusion principle, and Hund's rule. Right? The first principle, alpha principle. The word alpha in German means building up, kattamaittal, building up. The alpha, one more person. The word alpha, German means building up, The alpha principle. In the ground state of the atoms, carbon 6, so 1s2, 2s2, 2p2, the ground state electronic configurations. In the ground state of the atoms, the orbitals are, SPDF, the orbitals are filled in the order of their increasing energies. That is, the electrons first occupy the lowest energy orbitals available to them. In the ground state of the atoms, the orbitals are filled in the order of the increasing energies. That is, the electrons first occupy the lowest energy orbital available to them. The electron entered to the orbitals to the increasing order, the lowest energy to higher energy. Okay, you first fill in the lowest energy orbital, then fill in the higher orbitals. Once the electrons completely filled in the lowest energy, then the electron entered to the higher energy orbitals. For example, in carbon atom, the 1s orbital is a lowest energy orbital. First, completely filled in the lowest energy orbital, 1s orbital. So, completely filled in 2 electron in s orbital. Then the electron entered to the higher orbitals, 2s2 and 2p2. Are you right? So, the once electron entered to the once electron filled in the lowest energy, completely filled in the lowest energy orbitals. Then the electron entered to the higher orbitals. Okay, students. The filling of order of the various orbitals. The filling of various orbitals as per the alpha principle. It is in accordance with n plus L rule. Already you know that n plus L rule. N is the principal quantum number and L is the azimuthal quantum number. The principal quantum number n equal to 1, 2, 3, 4. K, L, M and N orbit. The L value, say L, S equal to 0, P equal to 1, and D equal to 2, and F equal to 3. The N plus rule. The N plus L value is least, the energy are also least. You write the lowest value of N plus L is the lowest energy, having lowest energy. You write N equal to 1 in first orbit, K orbit, N equal to 2 in second orbit, L orbit, N equal to 3 in M orbit, N equal to 4, K, L, M, N, O, P, Q. Right? So N equal to 1 in first orbit, K orbit, only one orbital is present, S orbital. So S orbital is 1s orbital, and second orbit N equal to 2. So S and P, 2s, 2p. Next third orbital 3s, 3p, and 3d. 3s, 3p, 3d. In fourth orbital 4s, 4p, 4d, and 4f orbital. 4s, 4p, 4d, 4f orbital. In fifth orbitals 5s, 5p, 5d, and 5f, and 5f vice versa on 6 and 7 and 8 orbitals. You write? So N equal to 1 in 1s orbital, 1s, N equal to 2, 2s and 2p orbital, then N equal to 3, 3s, 3p, 3d. The 3s right in the straight line of 2p orbit. 2p orbital. So 3s, 3p, 3d. In next orbit, fourth orbit, so orbital 4s, 4p, 4d, 4f. Right 4s orbital in straight line in 3p orbitals. Okay, so 3p orbital in straight line, 4s orbitals, 4s in 3d straight line in 4p, 4d, 4f. Next 5s orbital, 5s in straight line in 4p orbitals, 5s and 4d in 5p, the 4f in straight line 5d and 5f. In 6s orbital in straight line in 5p orbitals. Okay, 6s, 5d in straight line 6p, 5f straight line 6d, and 6p in straight line 7s, and 6d in straight line in 7p. Are you right? So the increasing order of the energy of increasing orbitals, 1s, next 2s, right? So first 1s, so least energy, second 2s, 2p, 2p, next 3s, 3s, 3p, 3p, next straight line, 4s, 3p, 4s, then 3d, 3d, right, 4p, 5s, straight line, so less than 4p and 5s, next 4d, 5p, 6s, straight line. So complete the straight line, 5p, 6s, next 4f to complete the straight line, 5d, 6p, 7s, then 5f, 6d, 7p, right, 4f, 5d, 6p, and 7s less than 5f and 6d and 7p. Okay, the electron enter to lowest energy orbital to higher energy orbital. In an atom, the electron enter to lowest energy to higher energy orbitals. Once the lowest energy is completely filled then the electron entered to the highest energy orbital. Right? For example, nitrogen 7. How many electrons in nitrogen? 7 electrons. Right? So the least energy, 1s2. The s orbital having maximum 2 electrons. P electron in 6 electrons. D electron in 10 electrons. The F orbitals in 14 electrons. Okay, so 1s2. So remaining 5 electrons in nitrogen. So 2s2. Next highest energy orbital, 2s orbital, 2s2. Okay, the next 2p orbitals maximum having 6 electron, but remaining only 3 electron in nitrogen. Already 4 electron is filled. Okay, so remaining 3. So 3 plus 2, 5, 5 plus 2, 7. Okay, the electronic configuration of nitrogen in an atom, the electron entered to the lowest energy orbital to highest energy orbital. So 1s2, 2s2, 2p, 3. 2p, 3. According to Alpha principle. The next principle, Pauli exclusion principle. Pauli exclusion principle. According to Pauli exclusion principle, no 2 electrons in an atom can have the same set of values of all 4 quantum numbers. Principal quantum numbers, azimuthal quantum number, magnetic quantum numbers, and spin quantum numbers. So no 2 electrons. Each orbital having maximum 2 electrons. No, the 2 electrons is an atom. For example, helium, 2 electrons. So no 2 electrons in an atom can have the same set of values of all 4 quantum numbers. Each electron must have unique values for the 4 quantum numbers. Each electron must have the unique values for the 4 quantum numbers n, l, m and s. The principal quantum number, azimuthal quantum number, magnetic quantum number and spin only quantum numbers. For example, for the 1 electron present hydrogen atom, 1s1, right? So 1 electron. For the 1 electron present hydrogen atom, the all 4 quantum numbers, the n equal to 1. The first orbit, so n equal to 1, l equal to 0 in s orbital, L0, M are also 0. Are you right? So the n equal to 1, L equal to 0 and M equal to 0 and S is equal to plus of. Already you know that. So only two value presents in SR. Spin only quantum. Only 2 values are there in spin only quantum numbers. Plus of, another one is a minus of. One plus of or minus of. Are you right? So the 1 electron present hydrogen atom, the 4 quantum numbers n equal to 1, L0, M0, S equal to plus of. For the 2 electron present in helium atom, helium 2. So 2 electron presence in the helium atom. So 1s2. 1s2. In 1 electron for 4 quantum numbers are in 1 electron for 4 quantum numbers. So n equal to 1. First orbit n equal to 1. So L equal to 0. L equal to 0 and M equal to 0 and S equal to plus of. In another 1 electron in 4 quantum numbers, n equal to 1. N equal to 1, L equal to 0, M equal to 0, and S equal to minus of the same set of 4 quantum number in hydrogen atom, for hydrogen atom in helium. In first electron in helium, the same 4 quantum number for hydrogen atom. N equal to 1, L equal to 0, M 0, S equal to plus of. But in another one electrons having different spin quantum number. Different in spin quantum number. So plus of, minus of. Are you right? So no, the 2 electrons in an atom can have the same set of values of all 4 quantum numbers. So differ in the 4th quantum numbers, spin quantum numbers. Each electron must have the unique values. Each electrons must have the unique value for the 4 quantum numbers. Do right? So already you know that the spin quantum number value only plus of or minus of. According to Pauli exclusion principle, each orbital having maximum 2 electrons. You right? So the K cell, L cell, you write K cell 1s orbital and L cell 2s and 2p orbitals. So 2s2, 2p6. Okay, so write the 8 electron in all 4 quantum numbers. You right? So let us understand this by writing all the 4 quantum numbers. All the 4 quantum numbers of the exist electrons in L cell. 8 electrons in L cell. Are you right? Okay. L cell S2, 2s2 and 2p6. Okay. So 4 quantum numbers of the 8th electron in L cell. Okay. L cell 2s2 and 2p6. 2s2, 2p6. The n equal to 2, L equal to 0, 1. 0 in s orbital, 1 in p orbital. The m equal to m equal to 0 in s orbital. So m equal to -1, 0, +1 in p orbital. Are you right? So in 4 quantum numbers of the 8th electron in L cell. So n value. Okay. So n value electrons. Electron, n value, L value, m value, s value. Right? In first electron, the first electron, s orbital, 2s orbital, first electron. So the first electron, n equal to 2, common. Second orbit, so n equal to 2. L equal to s orbital 0. N equal to s orbital 0. M are also 0. In first electron, s value plus of. Okay. The second electron, n value 2. Second orbit, 2s orbital. So 2. The L value in s orbital 0. Okay. In second electron. Okay. So m are also 0. The s value is minus of. Okay, the first electron in spin quantum number plus half, in second electron spin quantum number is minus half. Are you right? So next in p orbital, so third electron, the third electron presents in p orbital. Okay, so 1, 2, 3, 4, 5, 6, 7 and 8. 7 and 8. Are you right? The third electron, n equal to 2. So 2p orbital, n equal to 2, third and fourth, fifth, sixth, seventh and 8 electrons. Okay, so n value same. N value same. The second orbit, so n equal to 2. Okay, in third electron presents in p orbital, so p orbital L value 1, m minus 1, the third electron plus half. In fourth electron, in same 2p x orbit, 2p x orbital, so for 2, 1 minus 1 in minus half. Okay, so the different in fourth quantum number. Different in fourth quantum number plus half minus half. You right? So complete in third and fourth electrons and fifth electron. The fifth electron n value 2. The L value all p orbital n value 1, 1, 1, 1. Okay, s orbital L value 0, p orbital L value 1. Okay, so the 3 and 4th electron m value minus 1 and 5 and 6th electron m value 0, 0. Right? And 7th and 8th electron m value plus 1, plus 1. 7th and 8th electron m value plus 1, plus 1. Are you right? In fifth electron is clockwise direction plus half. In fifth electron clockwise direction and sixth electron anti-clockwise direction minus half. Right? So seventh electron is clockwise direction and eighth electron is anti-clockwise direction. Okay, so minus half. Right? So no, the two electrons in an atom can have the same set of values of all four quantum numbers. The fourth quantum number is vary. The fourth quantum number is vary. Are you right? So in each electron, the third quantum number, principal quantum number, azimuthal quantum number, and magnetic quantum number is same, but the fourth quantum number is different. You right? So the three quantum number is same. The three quantum number is same, but the fourth quantum number is different. You right? The next principle, Hund's rule. Hund's rule. The alpha principle explains in an atom the electrons enter to the various orbitals. The alpha principle cannot deal with the electron field in the degenerate orbitals. Degeneracy means the same energy orbital. P orbital, Px, Py and Pz. The three degenerate orbital in P orbitals in 1, 2, 3, 4, 5. 5 degenerate orbital in D orbitals and 7 degenerate orbitals in F orbitals. 1, 2, 3, 4, 5, 6 and 7. 1, 2, 3, 4, 5, 6, 7. Okay, so the degenerate orbital. How to electron field in the degenerate orbitals cannot deal with the alpha principle, that deal only Hund's rule. They explain only Hund's rule. According to Hund's rule, the electron pairing in the degenerate orbitals, the electron pairing in the degenerate orbital does not take place. The electron pairing in the degenerate orbital does not take place until all the available orbitals contain one electron. In p orbitals, the three available degenerate orbitals 1, 1, 1. Are you right? So the fourth electron entered to pairing. In d orbital 1, 2, 3, 4, 5. In available 1 electrons. Then pair up in 8 electrons only. Pair up 8 electron only. You right? So 1, 2, 3, 4, 5, 6, 7. 7 unpaired electron. Then the 8th electron entered to. So sorry. The 1, 2, 3, 4, 5. The 6th electron entered to pair up. In F orbital 1, 2, 3, 4, 5, 6, 7. The 7 unpaired electron, then 8th electron entered to pair up. The electron pairing in the degenerate orbitals does not take place until all the available orbitals contain one electron. Are you right? So first completely fill one electron, then pair up. To avoid electron-electron repulsion. For example, carbon 6. 1s2, 2s2 and 2p2. Okay, so in 1s orbital, 1s2 in 2s2. You right? So according to alpha principle, the electron filled in the least energy to higher energy orbitals. And Pauli's exclusion principle, the each orbital contain maximum 2 electrons, right? In 2p orbitals, and according to Hund's rule, are you right? So the electron pairing in the degenerate orbitals does not take place until all the available orbitals contain 1 electron each. Are you right? So 2px, 2py and 2pz. Say degenerate orbitals. The degenerate orbital contain unpaired electrons. First fill in unpaired electrons. 1 and 1. Okay, 2p2. To avoid the electron-electron repulsion. The pair of electron occur electron-electron repulsion. You right? So the next one electron occupied in the unavailable orbital. Electron not available orbitals. Vacant orbitals. Are you right? Okay. In another one example, oxygen. In oxygen, 8, 1s2, 2s2, 2p4. Are you right? So 1s2, 2s2 and 2p4. Okay, so the electron pairing in the degenerate orbital does not take place until all the available orbitals contain 1 electron. So p orbital contains 4 electrons. So 2px1, 2py1, 2pz1. Then pair up in 4th electron in 2px orbital. 2px orbital. Alright, the electronic configuration. Next one is the electronic configuration of atom. Electronic configuration of atom. The distribution of electrons. The distribution of electrons into various orbitals. The distribution of electrons into various orbitals of an atom. The distribution of electron. The distribution of electrons in the various orbitals. 1s, 2s, 2p, 3s, 3p, 3d, 4s. Okay, the distribution of electrons into various orbitals of an atom is called electronic configuration. It's called electronic configuration. So in an atom, the electrons are filled in the according to alpha principle, Paulian exclusion principle, and Hund's rule. Okay, the electronic configuration written as NLX. NLX. So N represents principal quantum number. Okay, so K, L, M, K1, L2, M3. The L represents azimuthal quantum number S, P, D, F, L0, 1, 2, 3. The X represents the number of electrons present in the orbital. Number of electrons present in the orbital. Right? For example, the one electron having atom, hydrogen, H1. So the electron present in first orbit, K. So N1. Right? So N1. So one electron are present in S orbital. So L0, S orbital. Yes. Okay. The number of electron, X, number of electron present in the orbital, 1. Right? The electronic configuration of hydrogen, 1s1. The orbital diagram, 1s1. 1s1. Are you right? So spoken as 1s1. Spoken to 1s1. Okay. So in another one example, nitrogen 7. Okay. So 1s2, 2s2, 2p3. 2p3. Right? So according to alpha principle, the electron entered to lowest energy to higher energy orbitals. Okay, so 1s2, 2s2, 2p3, and Pauli exclusion principles. Each orbital having maximum 2 electrons. So 1s2, 1s2, and 2s2, 2px. 2py and 2pz. 2px, 2py and 2pz orbitals. 2pz orbitals. You write according to Hund's rule. The electron pairing in the degenerate orbitals. The 2p orbital is a degenerate orbital. Same energy orbitals. So does not take place until all the available orbitals contain 1 electron. So 1, 1, 1 to avoid electron repulsion. Are you right? So already you know that oxygen atom. Okay. So next fluorine F9. 1s2, 2s2, 2p5. 2p5. Okay. So 1s2, 2s2, 2p5. 1, 2, 3. The fourth electron entered to pair up. 2px, and fifth electron entered to 2py orbitals. Pair up. You right? So the correct electronic configuration of fluorine, 1s2, 2s2, 2p5. The orbital diagram. Right? Right. The expected electronic configuration of some elements such chromium and copper. Chromium 24, copper 29. Some expected electronic configurations. The expected electronic configuration of some elements, chromium and copper, differ from an actual electronic configuration. Chromium 24, the expected. In expected electronic configuration, the expected electronic configuration of chromium 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2, 3d4, 4s2, 3d4, 4s2, 3d4. But in actual electronic configuration, of chromium 1s2, 2s2, 2p6, 3s2, 3p6 and 4s1, 3d5, 3d5, right? So copper 29. Okay, so expected electronic configuration of copper 1s2, 2s2, 2p6 and 3s2, 3p6, 4s2, 3d9. And actual electronic configuration of copper 1s2, 2s2, 2p6, 3s2, 3p6, and 4s1, 3d10. 3d10. You write the actual electronic configuration of chromium 4s1, 3d5 and copper 4s1, 3d10. According to Hund's rule, the half-filled and full-filled orbitals are more stable than partially filled orbitals. In other words, half-filled in p orbital 3, full-filled in p orbital 6, half-filled in d orbital 5 and full-filled d orbital in 10. In half-filled in f orbital 7 and full-filled f orbital in 14. So half-filled and full-filled orbitals are more stable than partially filled orbital P2, right? P2, P5, P2, P5, D4, D9. So D4, D9 and F6 and F13. You right? So the half-filled and full-filled orbitals are more stable than partially filled orbital due to stability. The 4s electron in one 4s electron occupy the 3d orbital. Are you right? In chromium and copper. So chromium attain half-filled d orbital and copper attain full-filled d orbital. So half-filled and full-filled orbitals are more stable. Are you right? So the actual electronic configuration of chromium and copper electronic configuration is slightly differ from actual electronic configuration. The expected electronic configuration is slightly differ from actual electronic configuration. Are you right? The one more question. The correct electronic configuration of chromium 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5. The correct electronic configuration of copper 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d10. 4s1, 3d10. Okay, students. The next one is the stability of half-filled and completely filled orbitals. The stability of half-filled and completely filled orbitals. The chromium and copper. Chromium 3d argon 3d5 and 4s1. Copper argon 3d10 4s1. The half-filled and full-filled orbitals are more stable than partially filled orbital 3d4, 4s2, 3d9, 4s2. The half-filled and full-filled orbitals are more stable than partially filled orbitals. Okay, so this stability can explain by using symmetry and exchange energy. Symmetry, and next one is exchange energy. Symmetry and exchange energy. The symmetrical distribution of electrons in degenerate orbitals. P orbital. In p orbitals, 3 degenerate orbitals. In d orbitals, 5 degenerate orbitals. In f orbital, 7 degenerate orbitals. So right, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5. 5 degenerate orbitals. The parts, the half-fill orbitals. In p orbital, d orbital, in f orbitals, half-fill and full-fill orbitals in p orbitals, in d orbitals. The half-fill orbital and full-fill orbitals. So, symmetrically distribution of electron in half-fill and full-fill. Then, partially filled orbitals. Then, partially filled orbitals. So, symmetrical distribution of electrons having more stability. More stability. For example, the degenerate orbital px, py and pz. Say degenerate orbitals having same energy, equal energy, but different orientation space. Different orientation space. X, y, z. Okay. X, 2px, 2py and 2pz. 2pz. The distribution of electron. The distribution of electron. The distribution of electron in half-fill. In half-fill. Due to the symmetrical distribution. Due to the symmetrical distribution. Due to the symmetrical distribution, the shielding of one electron. The shielding of one electron on the other relatively small. Are you right? The symmetrical distribution of half-fill and full-fill orbitals, due to the symmetrical distribution, the shielding of one electron. The shielding of one electron on the other is relatively small. And hence, the attractive force between the nucleus and the electron is more. The stability are also more. Okay, the symmetry distribution having more stability. The symmetrical distribution having more stability. The next one is exchange energy. Exchange energy. Okay, so two or more same spin orbitals in d orbitals. The two or more same spin, 1, 2, 3, 4, 5. The same spin orbitals. The two or more same spin orbitals having changed the position of the electron. Change the position. In each electron, change the position. The exchange the position, the energy are also released. Thus the energy, releasing energy is called exchange energy. Are you right? So, two or more same spin electron having exchange energy. To exchange the position. The electron exchange the position, that time the energy is released. The releasing energy is called exchange energy. The half-fill and full-fill orbitals are having more exchange. So more energy is released. So exchange energy is more, stability are also more. For example, chromium 3D 5 forest 1 in 3D orbital having 5 electrons. In another one, actual electronic configuration, in expected electronic configuration of chromium 3D4 forest 2. Okay, so 1, 2, 3, 4. The symmetrical distribution and half-fill orbitals. So unsymmetrical distribution. Partially filled orbitals, the exchange, the number of exchanges is possible. More exchange is possible in half-filled orbitals. Less exchange in partially filled orbitals. You write the exchange. The exchange of first electron 1, 2, 3 and 4. So 4 exchange in first electron. In second electron. In second electron, 1, 2, 3. 3 exchange is possible. In third electron, so 2 exchange is possible. 2 exchange is possible. The fourth electron, so 1 exchange is possible. The number of exchanges is 4 plus 3 plus 2 plus 1. The total number of exchange is 10. Total number of exchange is 10. But in 3D 4, in first electron 1, 2, 3. So 3 possible in first electron. In second electron, so 2 possible in second electron. In third electron, so 1 possible. Okay, so number of exchange 3 plus 2 plus 1, so 6. The half-filled chromium 3D orbital, the 10 exchange is possible, but 3D4 only 6 exchange is possible. So more exchange release more energy, is more stable. So 3D5 4s1 orbital is more stable than 3D4 and 4s2. 3D4 and 4s2. Right? Okay students. Thank you students. We'll meet next class.